Hello, everybody. My name is Gabriella Gilli, and I work at the Institute of Astrophysics and Space Science in Portugal. The work I'm presenting today is a result of collaboration with my colleagues at LMD, which is one of the IPSL laboratory in France. This is focused on the impact of non-orographic gravity waves in the middle atmosphere of Mars and Venus using general circulation models. Some of you are probably familiar with the characteristic of IPSL GCMs, which are developed for terrestrial planets and also exoplanets. In this talk, I will try to summarize briefly some characteristics of the simulation that I performed for Mars and Venus. Starting with Mars, this GCM is currently used to predict details of Mars climate system, including dust, water, CO2, photochemical cycles, etc. It's a ground to exosphere 3D models. However, the simulations I performed are extended up to the mesosphere, which is about 100 kilometers. The dynamical core is the same used for the Earth LMD GCM. And there are specific physical processes also included, like vertical distribution of dust, rotating particle clouds, and the parameterization of orographic and non-orographic gravity waves. Regarding topography, also we also take into account. And here on the left, there are some references, key references of this continuously updated model. Let's go to Venus. This is a ground to, the IPSL GCM is a ground to atmosphere GCM. Extended up to 150 kilometers. The dynamical core is the same as for the Earth and Mars. The state-of-the-art version that we use is currently high. Grid cells correspond to about 200 kilometers. And there are also specific processes that we take into account. In particular, for the upper atmosphere, we include non-LT processes, UV heating, molecular diffusion, etc. And the parameterization of subgrade processes. But so what is the interest and motivation of including those processes, subgrade processes in our GCM? As you know, gravity waves are an intrinsic feature of stably stratified planetary atmosphere. They've been frequently observed in the atmosphere of all terrestrial planets, and they are also known to play an important role in the transport of energy and momentum in the atmosphere of planets in general. For Venus and Mars, they are indicated to be responsible for high variation observed in their upper atmospheres. However, their primary source and basic characteristics are still an open question. It's thought that the gravity waves propagating in the upper atmosphere of those planets has a non-orographic origin, like convection from system jet streams. It means that those sources can generate waves through the full range of phase speed, wave frequency, vertical and horizontal scales. So considering that the approach that we use, which is a stochastic approach of subgrade dynamics following the work done on the Earth GCM, we think it's a reasonable choice because it represents the unpredictable aspects of subgrid dynamics when the source is not very well known. So our goal is to understand what is the impact of those waves on winds and temperature, what is the magnitude of the drag, and where the gravity waves break. Unfortunately, the gravity waves are highly unconstrained by observations. Their impact on the global circulation of Venus and Mars is still under investigation. We have to start with several assumptions. One of the assumptions is that the source is uniform. There are no latitudinal variation. We assume that the main source is convection. This sketch for the Venus atmosphere, you see here that the convective cells are located in the middle of the cloudlet, which is around 55 kilometers for Venus, and for Mars is about 8 kilometers, depending on the topography. And at those fixed altitude, the waves are launched upwards. They can be both eastward and westward. So we have implemented in a non-orographic gravity waves parameterization, which was previously developed for the RGCM. I don't have time to enter into details in this parameterization, but you can find the details in those reference papers. I've tried to summarize here the main steps. Basically, the main fields like temperature, pressure, winds, physical time steps are given by GCM. Then we have to initialize the basic parameters of the gravity waves using this stochastic approach, as I mentioned. Where a large ensemble of monochromatic waves is generated at a fixed altitude. In other words, the frequency, the horizontal wave number, the phase speed, etc., are chosen randomly, but with a prescribed box shape probability distribution. Then we deduce the vertical momentum flux using this expression. And this approach allowed to the model to treat a large number of waves at a given time step by adding the effect of those waves to the waves launched at previous time steps in order to compute the tendency as it's indicated here. So we have the drag on the winds, on the zonal winds, can be acceleration or deceleration, depending on where gravity waves encounter critical levels. I have summarized here the main tunable non-orographic parameters used in the model. On the left and on the right, the two tables represent the wave characteristic use and reference simulations for Venus on the top and for Mars on the bottom. Consider that as much as possible, we try to fix the minimum maximum level, values according to a few observations that we have. So let's have a look to the results. Let's start with Mars. I have, for a section of time, I have selected just a few plots. Here, this figure represents the seasonal variation of diurnal tides in the tropical region of Mars. It's a function of pressure and solar longitude. This is for Martian year 29. As I mentioned before, we have to take into account that gravity wave basic characteristics are highly unconstrained. So our strategy was to fine-tune the parameters by comparing model simulations, particular temperature simulation with data taken with Mars Climate Sounder, MCS, which are the best systematic temperature measurements in the middle atmosphere of Mars so far. So in the top panel, you have the MCS data. In the middle panel, model simulation without gravity waves. And on the bottom, the simulation when the gravity wave scheme is on. As you can see, at above 10 Pascal, both the amplitude and intensity of thermal tides simulated with the model without the gravity wave parameterization were higher than observed. And with the inclusion of gravity waves, we can have a better representation of the temperature. We have also to say that this improvement and the temperature, this change in the temperature is relatively moderate. It's about 10 to 20 Kelvin compared to the impact that we have on the zonal winds, as we will see in the next slide. Here in this figure, I show the mean zonal wind as a function of altitude and latitude. The top panels here, without gravity waves and with gravity waves on the right, the gravity wave drag and the zonal wind differences. Notice that here in the presence on wind jets, it's where we have a stronger drag of gravity waves. It's where the gravity waves drag moment deposition occurs about 50 kilometers around here. And for a given gravity wave phase speed, the drag is stronger, is larger in the present wind jets, where the intrinsic speed is also larger. So we can basically, the effect is to reduce the wind jets at middle latitudes. Let's have a look at the results for Venus. Sorry, I have just selected a couple of figures obtained with the IPSL Venus GCM. Here, there are temperature and zonal winds cross-section, latitude versus local time at this particular pressure layer, which corresponds to about 105 kilometers. Before the implementation of gravity waves, as you can see here near the morning terminator, we were simulating this cold pool, which did not observed, and these strong equatorial jets, which was strongly reduced after the implementation of gravity waves. In addition, also gravity waves were reducing supersonic winds, subsolar antisolar winds in the upper atmosphere. And as a result, we have, we can say that this parameterization as for Mars were reducing the stabilities and improving data model comparison. However, I would like to give some word of cautions. In fact, we found that the GCM is highly sensitive to unconstrained gravity wave parameters, as you may imagine. And in this example, it just tests as an example that they did varying one or two of these tunable parameters. And the result is impressive because you can see that these are zonal mean wind profiles at the equator, so they are average zonal means. But the effect of gravity waves can even reverse zonal winds from westward to eastward. So depending on the characteristic, there is a huge difference of not only of circulation in general in the upper atmosphere. And well, we have to be very cautious because it can also produce sometimes unrealistic results. To conclude, this is a summary and conclusion of this talk. Well, the impact of non-orographic gravity waves in the middle atmosphere of terrestrial planets is not negligible. We should include them in our models. The stochastic approach is a reasonable choice when the primary source is not very well known, because well, it allows you to treat a large ensemble of waves with different characteristics. In Venus and Mars GCM, we found that gravity waves parameterization improves the representation of thermal tides, zonal winds, and thermal structure, and the mesosphere and thermosphere. Therefore, this is a very interesting, useful button that we have, but we have to be very careful in the choice of the parameterization. GCMs are highly sensitive to those parameters, and of course the choice is not straightforward. We have to try as much as possible when observations are available to constrain those parameters with observations, or try that the values are physically consistent. And I conclude my presentation here. Thank you very much for your attention. Bye-bye.